Hi everyone, welcome to the last video for week 1 on measures of spread or measures of variation. Measures of center, mean, median, mode, do not tell the complete story of a set of data. It's possible for several sets of data to have the same measure of center, but not have the same shaped histogram. Researchers also need to know about how spread out the data is. Statisticians have several ways that we can measure that spread outness or the variation in the data. We've already seen one of these. It's called the interquartile range, that distance from Q3 to Q1. Another measure of spread is called the range, which is the distance from the min to the max. So these two measures of spread are pretty quick to calculate. The range we can do in our head, biggest value minus smallest value. The IQR we can pull from that 5-number summary, Q3 minus Q1. The standard deviation is kind of like the gold standard for measuring spread in a data set. So this is the one that we're going to use the most. It is the most common, and what it's measuring is how far data values are from the mean. So the standard deviation is looking at how far each data value is from the mean. The standard deviation provides a numerical measure of the overall variation in a data set. So it looks at it looks at the distance from the mean for each individual data value and gives us an overall view of what that looks like. And it can be used to determine whether a particular data value is close to or far from the mean. So again, standard deviation, measure of the overall variation in a data set. So we look at the distance from the mean for each data value, and then we kind of summarize that in one single value that provides us an overview. Because it is based on the idea of distance from the mean, and distance is always positive or 0, your standard deviation is also always going to be positive or 0. And when the standard deviation, or SD for short, is small, that tells us that the data values in the set are kind of clustered pretty close to the mean, and the overall variation in the data set is low. So the data set's not very spread out. It's not taking up a huge amount of room on a number line. When the standard deviation is larger, that tells us the data values are more spread out from the mean. And there's more variation in the data set. So in a data set with a larger standard deviation, we're going to expect to see a dot plot that is not a dot plot. I just had a brain fart. A histogram that is taking up more room on a number line. And those minimum and maximum values are going to be further apart. So the overall data is more spread out, taking up more space on a number line. Just like the mean, we have notation for standard deviation to make the distinction between sample and population values. And just like the mean, we're going to use an English letter for the sample value and a Greek letter for the population value. And that's pretty consistent throughout all of statistics. English letters for sample values, Greek letters for population values. So for the sample standard deviation, we use S, or sometimes S sub x, to indicate that it's the standard deviation for a single variable x. We will come back to this type of notation later, but this notation here, S sub x, is the notation you're going to see on the TI-84s. For population values, we use the Greek letter sigma. It looks like an O with a long tail in front. And just like the sample symbol, you can just write sigma, or you can write sigma with a subscript x. It is important to note that unlike the mean, the sample standard deviation and the population standard deviation are calculated differently. Meaning when you look on a calculator, it's going to spit out a value for S and a value for sigma, and those values will be different. So it's very important for standard deviation that you are clear about whether you're looking at sample data or population data, because that's going to affect the number you pull from the calculator. When in doubt, it is probably an S value. Like 99% of the time that we're calculating a standard deviation, we're calculating it based on sample data. So if you're unsure and the problem didn't make it clear, the safe bet is it's a sample standard deviation, it's an S. But keep your eyes out for keywords that indicate you're looking for a population standard deviation or true standard deviation. So calculating the standard deviation, much like calculating the mean for grouped data, can be done by hand. There are formulas for it. We're not going to do that. I am going to introduce the formulas here so that you can see that they are in fact different, but I'm not going to ask you to use them. There is an example in the textbook, and I'm happy to go over that during office hours. I actually think it's kind of a neat calculation, but it is kind of tedious and requires you to be very organized. So I'm not going to test you on that. So calculating the standard deviation, if x represents a data value, then the difference between that data value x and the mean is called its deviation. Each data value has its own deviation because each data value has a different distance from the mean. That deviation for each data value is used to calculate the standard deviation for the entire data set. So standard deviation is based on this idea of an average deviation for each of those data values in the data set. The formula for the sample standard deviation is S equals the square root of the sum of the deviation squared divided by the sample size minus 1. So there is some symbology in there. That letter that looks like a broken E is the capital Greek letter sigma. And in math class, that means sum. It's telling you to add a bunch of stuff together. Specifically, in this case, we're adding the deviation squared for each of the data values in the data set. So for every number in the data set, you're going to subtract the mean from it, and then you're going to square it and add them all together to get the numerator. Some of why we're doing that, we're squaring the deviation because we don't want negatives. Distance from the mean should always be positive. We talked about that earlier. And then adding them all up and dividing by how many we have is an averaging process. That looks kind of like a mean calculation. And then taking the square root undoes that square. So that's kind of what we're doing. It is a rough approximation of an average. So you can kind of think of a standard deviation in that way. We've kind of averaged out the individual deviations to get an overall measure of how spread out our data is. The population standard deviation looks pretty similar. We're using that Greek letter sigma, lowercase sigma. We can see the deviation here, data value minus the mean. But in this case, we're doing the entire population size in the denominator. And again, I am not expecting you to memorize these formulas. I am not expecting you to use them to calculate anything. I just want you to have seen them. So if you see them in the future, you can go, oh yeah, that's that standard deviation thing. Again, you want to see how it works by hand office hours. Otherwise, let's go ahead and talk about calculators. If you're using TI-84, you already know how to do this. It's the 1var stats process. We're going to be using that an awful lot over and over and over again. The TI calculator calculates both the S and the sigma value at the same time, so make sure you're pulling the correct value. You probably want that S sub x. For GeoGebra, it starts similar to all our other things, enter the data in a list, but then there are two separate function calls. If you're looking for the sample standard deviation, it's just stdev for standard dev, and then the list name. If you want the population value, you have to tell it standard dev p, stdev p, and then the list name. So it's a little bit harder to mess that one up because you have to be intentional about which one you're calculating. Let's go ahead and do an example. So standard deviation example in a 5th grade class, the teacher was interested in the average age and the sample standard deviation of the ages of her students. So measures of center, measure of spread. The following data are the ages for a sample of 20 5th grade students. The ages are all rounded to the nearest half year. Find the mean and standard deviation for this sample of 5th graders. Then find the age that is 2 standard deviations above the mean. Okay, so we're asked to do 3 things: mean and standard deviation, and then find the age that's 2 standard deviations above the mean. Let's clean up our screen, shift this up a little bit. So here's our data, here's our set of directions, here's a list of the things we're looking for. And there's a very important keyword here. Specifically, this says sample. So I know when I get down to that standard deviation step, I'm looking for the S value. We are going to go ahead and use our calculator. Again, I'm going to pull over my TI-84, and we want to start entering that data. So stat edit, and then we're going to type that list of data into list 1. So fast time skip ahead, you can see that I've got that last data point in my list. If I go up to highlight it, you can see that it's the 20th data point in the list, which is good because we were told we took a sample of 20 5th graders. And we're ready to run that 1var stats call. So stat, calc, enter. My data is in list 1. This is raw data, so I don't have a frequency list. And then I run the calculate. And this spits out 2 of the pieces of information I need right away. The mean is 10.525. I'm going to round that to 10.53. Original data is 1 decimal place, so I want 2 in my answer. And then I'm going to go down to SX. I want the sample standard deviation. And that's 0.715, blah, blah, blah. And just like the mean, I want it to 2 decimal places. So 715 is going to round up to 72. So 10.53 for the mean, 0.72 for the standard deviation. The last step says find the age that's 2 standard deviations above the mean. Meaning I want to take the mean and add 2 standard deviations to it. So 10.53 is the mean, and then I'm adding 2 standard deviations, 2 times 0.72. and I get 11.97, which is bigger than the oldest kid in the class. So we're going to talk briefly about how to interpret that. But let's go ahead and make some notes. First, grouped data is the same procedures as it was for the mean. For TI-84, you do it exactly how you did the mean for grouped data. For GeoGebra, same process. Make the two lists, find the midpoints, enter the frequencies, except now you're using that standard dev or standard dev p function call. What I'd like you to do, pause the video really quick, and try to use the calculator or app of your choice and find the mean and standard deviation, and then the value that's 2 standard deviations above the mean for this set of baseball team ages. Okay, so when I did it, I got a mean age of 30.7. I got a standard deviation of 6.1. And 2 standard deviations above the mean would be 42.9, which is the 30.7 plus 2 times the 6.1. We use standard deviations to make comparisons for data from different data sets. So the standard deviation is useful when we want to compare data values that come from different data sets. If those data sets have different means and different standard deviations, we can't do direct comparisons. Those direct comparisons are not going to give us an accurate picture of what's happening. To avoid this, we use something called z-scores or standard scores. A z-score counts how many standard deviations away from the value. I am so sorry. Counts how many standard deviations away from a data value is from the mean. That was a lot of words there. What we're doing is we're taking that deviation, distance from the mean, and we're turning it from a raw number into a number of standard deviations. Is it 1 standard deviation from the mean? Is it 2 standard deviations above the mean? Is it 1.5 standard deviations below the mean? To do that, we find that deviation, data value minus mean, and then we divide it by the standard deviation. If you've run 1var_stats to find the standard deviation, you should already have the mean as well. So running this calculation is just subtract and divide, subtract and divide. For a sample, you're using x bar and s. For a population, you're using mu and sigma, but you'll notice the resulting calculation is the same regardless. So it's data value minus mean divided by standard deviation. Let's do a quick example so we can see how this is useful. So 2 students, John and Ali, from different high schools, wanted to find out who had the highest GPA when compared to their school. Which student had the highest GPA when compared to the rest of their school? So from the table, we can see John had a GPA of 2.85. The school average was 3.0, and the standard deviation for his school was 0.7. On the other hand, Ali's got a GPA of 77, a school mean of 80, and a standard deviation of 10. So right off the bat, I can see that John's school and Ali's school are using completely different grading systems. That means that I can't compare their GPAs directly. So we're going to look at z-scores. Where is John relative to his mean? Where is Ali relative to his mean in terms of standard deviation? So z-score formula, data value minus mean divided by the standard deviation. So for John, his data value is this GPA 2.85 minus the mean of 3 divided by the standard deviation of 0.7. And I got negative 0.21. That negative z-score tells me his GPA is less than the school mean. If we do the same thing for Ali, we get Ali's GPA of 77 minus his school's mean of 80 divided by his standard deviation of 10. And I got negative 0.3. So much like John, Ali is a little bit below his school mean. If we plot those two negative numbers on a number line, John's z-score of negative 2.21 is higher, it's more to the right on the number line, than Ali's score of negative 0.3. And since we're looking at GPAs, higher values are considered better GPAs. So we would conclude that John has a better GPA relative to Ali based on their school grading systems. Okay, there's two slides here. I'm going to pop them up. I'm not going to talk about them right now because we're going to see them again. But there are two rules that talk about the distribution of data based on standard deviation. So Chebyshev's rule applies to the distribution in any set of data. It can be perfectly symmetric, it can be skewed, it can have 2 peaks, it can have 5 peaks, it can be flat or uniform, and Chebyshev's rule will apply. And what Chebyshev said is that at least 75% of the data should be contained within 2 standard deviations of the mean. Meaning that if I look at 2 standard deviations below, up to 2 standard deviations above the mean, at least 3/4 of the data should be between those two values. At least 89% of the data should be within 3 standard deviations of the mean. So if I go 3 standard deviations below and 3 standard deviations above, almost 90% of the data should be between those two numbers. At least 95% of the data should be within 4.5 standard deviations of the mean. So we go 4.5 below to 4.5 above. That's 95% of all of the data. If we are looking at a graph that is symmetric, more specifically, it is a graph that is symmetric and bell-shaped, meaning the peak is right smack in the middle and it trails off symmetrically in both directions. We can use something called the empirical rule. So the empirical rule only works for symmetric bell-shaped distributions. And in that case, more of the data is going to be closer to that peak in the middle. So approximately 68% of the data should be within 1 standard deviation of the mean. So more than half of all people would be within 1 standard deviation of the average height for humans. Yeah. Approximately 95% of the data is within 2 standard deviations of the mean. So if we know that height is bell-shaped and symmetric, then approximately 95% of people are within 2 standard deviations. Approximately 99.7, so almost all of the data, is within 3 standard deviations of the mean. We're going to be looking more closely at the empirical rule over the coming weeks because it turns out that there's a fair amount of data that can be described as symmetric and bell-shaped, And even if the data itself isn't symmetric, we're going to look at something called a sampling distribution. And oftentimes sampling distributions are symmetric even when the raw data is not. So we're going to be seeing a lot more of the empirical rule, but for now it's just good that you've seen it and you have a rough idea that for symmetric bell-shaped graphs, we expect that most people are going to fall within 2 standard deviations of the mean. Okay, if you have any questions on anything from week 1, shoot me an email, send me a text message. Both contact pieces of information are on Canvas, or you can drop by my office hours Thursday night from 7 to 8 p.m. or email me to set up an appointment. The link for office hours is on the week 1 videos and links page. And I hope you have a great rest of your week, and I will see you on Monday.